Mobility is the essence of our daily lives, defining how we access work, school, food, friends, and more. Through a century of various policies, most households have been socially engineered into car dependence that reinforce historical inequalities. Car ownership represents the second largest household expense, impacting household affordability. About 30% of the population cannot own and operate a car, legally, economically, or ability-wise. The transportation sector is the top 1 or 2 contributors to carbon emissions. Air pollution and the sedentary nature of car dependency have real health impacts and more. Which is why this project focuses on the use of bicycles and scooters, known as micromobility, as distance-spanning, point-to-point, small footprint, low-carbon, cost-efficient transport. On their own, or when combined with transit, these modes round out a complete suite of transportation options that can help most households reach most destinations within urbanized areas. More specifically, we're focusing on traffic signals as a critical pinch point that prevents new networks of micromobility infrastructure to function as seamlessly, safely, and conveniently as our system for car-based transport does. It turns out that it is quite complicated to make traffic signals better respond to changing policy goals, which is where this work comes in. Specifically, our project has 2 key pieces. First, to implement a new cloud-based, smart micromobility-capable traffic control system on one of the highest decorated need corridors in Portland, Oregon. Second, to use a unique multimodal simulation lab to make a digital twin of this corridor to remodel different scenarios, such as maximizing green waves or minimizing social clumping at red lights, to speed up the implementation process with confidence. Transit efficiency through this corridor will also be studied. Making traffic signal systems smart for non-car optimization is complicated because the traffic controller as well as the street are usually managed by local government, which is why we're thrilled to have the City of Portland as a partner. Micromobility is often provided by the private sector, and one of the leading micromobility providers, Lime, is also a project partner. Traffic signal systems are built by private sector companies, which is why Q-Free, with their broader understanding of transportation, is a partner. Road user sensors are also built by private companies, so we have included FlowCube as a partner. And transit is usually provided by quasi-public agencies with their own systems, and thus, TriMet is also a project partner. Given this complexity and that the status quo is focused on the movement of cars, universities become the logical place to test out alternate possibilities, partnering with diverse stakeholders in the process. The capacity to replicate and scale up this work is immense. Corridors are how cities plan transportation and land use. In fact, Portland has 5 other corridors primed to replicate this project immediately if successful. And nationally, there are over 300,000 traffic signals along corridors in all types of communities being otherwise retrofitted for micromobility. We are excited about this work and the potential for it to help expand mobility options to a greater range of the population, so that access to jobs, schools, food, recreation, and more is easier, more affordable, safer, healthier, done with significantly less carbon while being much more space efficient. It really is time to build back better.